All right, so today we're going to be looking at two things, Coulomb's law and electron configurations, to try and explain where electrons sit around an atom. All right. So as a little bit of review, remember atoms are made out of three things, protons, neutrons, and electrons. The electrons are a small subatomic particle with a -1 charge. Negative charge is really important to remember here, and it's found in these electron orbitals on the outside of the atom. Okay. The protons are positive and they're in the inside, and then the neutrons are also in this nucleus, this inner part, and they're neutral, they have no charge. Okay. So Coulomb's law is a way to describe how electrons and protons attract or repel each other. So Coulomb's law is a way to describe the force between charged particles, which depends on the magnitude, that means like the strength of the charges, and the distance between the particles, right? You can imagine this like our moon, if it were closer to the planet Earth, would feel a lot stronger gravity pull, right? Gravity would pull the moon in closer, we might collide with the moon. Or if another sun came around, our Earth would be pulled by its gravity towards it. So it's only if it's close enough, though. So that's why the distance matters. So when two magnets come together, right, we can see that the closer they get, the stronger the force between them becomes. Okay. These particles can have a positive charge, +1, +2, +3, depending on how many electrons they've lost or gained, or negative charges, -1, -2, -3. Key thing here, particles of opposite charges attract, so protons and electrons attract, they're positive and negative, but particles of the same charge will repel. So when two electrons are next to each other, they're both negative charges, so they will repel from each other, kind of like these magnets will repel from each other. All right, so these can represent electrons and their negative charges repelling. Okay, here's a little animation to visualize this. This attraction over distance increases in strength. So they're pulled closer, 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 bang, they're pulled together. Right? If you have stronger charges, this pull is even stronger. Okay, so if you have like a +2 and a -2 charge, that's a way stronger pull than a -1 and +1 charge. Okay. So the strength of the charges matters and the distance matters. Okay. So you can also see this with magnets. So this Coulomb's law describes strength of charged particles, electrically charged particles, but we could also apply this same concept to magnets. So here these two magnets are pushed together. They don't really feel an attraction until they get close enough, and then suddenly they're pulled with extreme force and they smash this apple. And actually the force is so strong the magnets break. So the further you are apart, the less attraction. The closer you are together, the more attraction. Okay. As a visualization of repulsion, right, if we have a positive charge next to a positive charge or a negative charge next to a negative charge, they will repel away from each other. Right, they will separate until they're so far apart that they no longer repel anymore. Okay, kind of like these magnets here. If I lift up this magnet, I don't feel it repelling off this other one anymore. But if I push it down, I can feel that repulsion getting stronger. I have to press harder in order to force them together. Okay, so now Coulomb's law helps us describe how electrons are arranged in an atom. So the force between charged particles, namely electrons and protons, depends on the magnitude of the charges and the distance. Okay? So these negatively charged electrons attracted to positive protons in the nucleus, but they're also repelled by other negative electrons. So when these electrons are pulled to the nucleus, they are sometimes shielded or blocked. You can think of like in football, somebody might block someone who's running to keep them from getting to a goal. In this case, the goal is the nucleus. That's where they're being pulled to, and the other person blocking them keeps them from getting there. Same thing here with electrons. So when electrons in the outer parts of the atom are being attracted to the inside, they're also being repelled by electrons on the inner layers. So only some of the electrons can actually be close to the nucleus. So to represent this a little more clearly, I got these magnets, which magnets can attract or repel from each other the same way that charged particles can. So if we take, right, and we set one of these down, right? This electron gets pulled all the way down to this base. Let's call this base our nucleus. It's got positive charge. This electron's got a negative charge. If I let go, it gets pulled all the way to the innermost layer of the atom. We call it the first energy level. Then if I keep adding electrons, notice they get pulled down as well. In this case, gravity is representing that attraction. But they have to stop because they get repelled by other electrons. Okay? But if we keep going, right, what we'll find is that each layer has to be further and further away from the nucleus, right? Further and further away until we have a large stack of what we call energy levels or shells. And each of these shells can hold a certain number of electrons getting further and further away from the nucleus. If an electron gets too close to the nucleus, it feels a stronger repulsion because its distance from other electrons decreases as well. So then it gets pushed back. If the electron stretches out too far, right, now it feels a stronger attraction. The repulsion from other electrons decreases, and it will pull back into the nucleus. So this is a way of describing how Coulomb's law explains that electrons can arrange themselves in these stacks around the nucleus. So if we keep going here, all right, these electrons, because of Coulomb's law, are pulled to a nucleus but repelled by other electrons, and so they sit at predictable distances from the nucleus. These predictable distances we call energy levels. And we sometimes represent them with these rings. Electrons don't actually move like this, but this is a useful way of looking at these different levels. So this bottom level here, this bottom magnet, we can call the first level. And here you can see 2 electrons. We'll talk about why there's only 2 in the first one. But then there's a second energy level, okay? This second stack, all right? It can't be as close to the nucleus because it gets repelled. But this can hold 8. Don't worry about memorizing that. And then we have this third energy level, this fourth energy level, and I've got a fifth one here, but cobalt actually only has 4 energy levels, which we sometimes just call shells. Okay? So these electrons, these small particles with negative charge, arrange into energy levels 1, 2, 3, 4, 5, 6, which is actually the same as the period number that the atom is in. So, since Coulomb's law depends on distance, this also represents the energy of the electrons. If I want to pull this top magnet off, it's super easy, right? It's not super heavy. This next magnet, I have to pull a little bit more, and a little bit more, and a little bit more, and then this bottom one is actually kind of challenging to pull up. Like, I can still do it, but it takes a lot more energy to remove electrons from this innermost energy level than it does from this outermost energy level. You can feel the difference here, and you're welcome to use this in class. Okay. We give a special name to these electrons at the very top. All right, these ones are really special, and we'll talk about them a lot more. These are called valence electrons. Right? What this means is these are just electrons in the outermost shell. Right? So for cobalt, the outermost shell is this 4th energy level here, and this 4th energy level for cobalt only has 2 electrons. So if we were to describe cobalt's valence shell, its valence energy level, it has 2 valence electrons in its valence level. Okay? All of the other electrons we call core electrons because they're on the inside, right? They're in the core, kind of like the core of the Earth is on the inside and then the crust is on the outside shell of the Earth. If we were to describe the number of core electrons here, we'd say there's 24 core electrons. So underneath that valence shell, there's 24 more electrons. Okay? So let's do a little practice here, all right? Just practicing with energy levels. This stuff does get more complicated as we go. But if we're looking here, right, on the left, we've got an atom of lithium here, okay? How many valence electrons does it have? Well, let's look at the outermost level. This is the outermost level, okay? So it's got 1 energy level, and inside of that energy level, we have 2 electrons. Okay, we got 1, 2. For this atom over here, right, it's got 1 energy level, then a second energy level. So it's got 2 total energy levels. Its outermost energy level has 4 valence electrons. Okay, so valence electrons are really important. It's a very key topic that we want to remember for the future. We'll be returning to it a lot.